So last time we proved this theorem by GKKS 2014, which is for the depth 4 model where both the product fannins are restricted. So the bottom product fannin is B and the top product fannin is n by B, and we intend to produce a polynomial of degree n, and the number of variables will be n square. So that it's an anomaly. So here the number of variables is actually different, because this is for the determinant. So it's an n square variate degree n model. Product fannins are restricted. So with these assumptions, we showed that the size required, or even the product gates required in the top, this is 2 raised to n by b. Okay, so if you take b to be square root n with the balanced version, then you get 2 raised to square root n, and you know a construction n to the square root n. Okay, so this is nearly a lower optimal lower bound, and hence the depth 4 reduction is also optimal. Right, so this requires the new tool of shifted partials. This result was followed by many others. In particular, so this was further improved. By a result where the polynomial was changed. So instead of determinant, they used something else, which is basically iterated matrix multiplication. Determinant is also in VP, right? It's a VP polynomial. So what this result is showing is that a VP polynomial which is hard for this model, right? So this is still away from the original goal of VP versus VNP. So we are already starting with a kind of easy polynomial, a VP polynomial, and the same thing in this result also, but it will be iterated matrix multiplication. It's again in VP. So theorem 1, theorem 2 is by Fournier, Lemay, Malo and Srinivasan. So any sigma pi circuit, again size is S, this is, we go root D and this is root D, circuit computing iterated matrix multiplication. So n by n matrices and D many, right? So degree is D of the polynomial. Number of variables is n square D. So for this polynomial, the size will be n to the root D. So improvement is in the base. So instead of 2 raised to root D, now you are getting n to the root D, which is truly optimal. So you can actually write iterated matrix multiplication as sigma pi model in n to the root D, and you cannot do any better. So depth 4 reduction is truly optimal. That's what you get, because this is in VBP. Right, so it's an even simpler polynomial. So this is a stronger result.
The technique is same for this one?
Yes. You have to prove a lower bound for IMM. That needs more specialized analysis. There is some assumption on D, so D is assumed to be n to the delta for small delta. So D is delta will be chosen accordingly in the proof. So ultimately D will be some n to the some fraction. That's not very important. The result you will get will be n to the square root D, and you also have a circuit of this size. Okay, any questions? So that shows the optimality. So I will not prove this because this will again be a very specialized analysis, just like what we did with shifted partials of determinant. Here you have to do it on IMM. We'll skip this, but it can be read.
So of course it's also on the size of the circuit, but is it also result saying that you need this much top fan in as well?
Yeah, that is S.
That is the S one.
S is the top fan in this. Because the proof method is like that. In the upper bound you get S times something. S is the top fan. Okay, so now we'll move to another result which will require us to change the measure a bit. So this will be homogeneous depth 4 model. So using these techniques there have been many results, cover all of them of course, but see the representative ones. So homogeneous depth 4 is by itself also an interesting model, and it is a restriction, right? So when you are looking at constant depth, then it is a restriction. If you look at unrestricted depth, then it is not a restriction, because in unrestricted depth you can separate the homogeneous parts by Strassen's homogenization theorem. In constant depth you will not be able to do that. Sorry?
This prove that in constant depth we cannot.
No, there is an absence of proof. How do you do? Yes, so how in that in the way you extract the homogeneous parts,
Is that a simple circuit? You look at the original circuit and you build up at each node, compute the homogeneous three parts and compute at each node. So it's like depth is almost like you're copying the circuit but a little differently. Look at each node and then you.
so you are saying that the depth doesn't change?
I mean, yeah, it should not change, it should definitely not decrease. It increases.
By how much?
By
You have to
prove that it will
increase.
Then you can't depth reduce. Every multiplication you replace by.
No, but can you reduce depth 4 circuit to a homogeneous depth 4 circuit?
Every homogeneous depth 8 or something.
Exactly. So
And depth 4 is quite compact itself.
so homogeneity is a restriction. Yeah, so depth may slightly increase. Homogeneity is a restriction for constant depth. But not for general circuits. So this is then a different model. It will need a new proof. This result will not follow from the previous result, because in the previous result we have said that A and B are bounded. I mean A and B are upper bounded by a function that we had fixed. By homogeneity, you don't get that automatically. So the method has to be different. So if a homogeneous sigma pi A, sigma pi B computes a degree D polynomial f, then we get, so all we can deduce is that A and B are both less than equal to D. We cannot claim anything better, right? Because in some product gate it can be A can be 1 and B is D. In some other product gate it can be the opposite. A is D and B is 1, right? So you cannot claim anything better than this. So this is, then A and B are kind of very high. So the question is, can we still use shifted partials? So the problem with shifted partials is that in its lemma 1, which was the upper bound, you will get a trivial upper bound if you take AB to be D. So that will not see anything special about the model. So that has to change. Yeah, just to remind, I think let us define the model properly. So in a homogeneous depth 4 circuit, take it as a definition. In a homogeneous depth 4 circuit, f x1 to xn being computed like this. Where Qij is a homogeneous sparse polynomial. Yeah, I'm using the word sparse, but this is just to signify that all the monomials in Qij will be counted. So whatever monomials appear, they will count. Monomials that don't appear will not be counted. Okay, so the actual support will be counted in the size, overall size of the model. So Qij's are explicitly given, then you multiply them and add them. Okay, that computes f equals f, and the degree of Qij for a fixed I this is equal to the degree of f for every I. Okay, f also is homogeneous. So that's the definition we'll take, that it's a depth 4 circuit where every factor is homogeneous, and in a product the sum of the degrees of the factors is degree of the polynomial being computed f. So the addition gates will also be adding up equidegree monomials. So that's our model. I want to get a lower bound for this.
So at least the previous lower bound will hold. That means.
There is no previous lower bound. AB is D.
Suppose
Both A and B are D. So right now we have nothing for this model. Seems to be a hard model.
Could you please explain why, again, why these, we expect these Qij's to be homogeneous polynomials?
What do you mean expect?
Sparse.
No, this is a definition. There is no expectation.
But why is sparse? Why sparsity is coming into picture?
Well, sparse just means that if the size is T, then there are only T monomials. Sparsity just signifies the fact that the size will include each and every monomial that appears, and we don't count monomials that don't appear. So when we also count them, then sometimes we call that dense polynomial. Sparse polynomial is basically sigma pi. So formally, we can also think of this as the sigma pi model. So it's a sum of products, and as many products you have, that is the size of Qij. So Qij's are depth 2, and then you multiply them and add them, so you get depth 4. So those are the things in the definition, and so since we don't have anything about A and B, I mean in general in depth 4 A and B could have been arbitrarily large, so at least that has been restricted. It cannot be more than D, but still D is quite large as far as our measure is concerned. Our measure fails at that regime, in that regime. So one thing that we will use in the proof is that Qij's have few monomials. That will be used. Yeah, so I think I should at this point not use S for the top famine, because S will really be total size in our proof from now on. Let's call it S prime. So now what we will do is, if the total size is S, which will also include how many monomials appeared in Qij, we have to use that fact. We have to use the fact that Qij has few monomials, and then try to do something. Basically in the end we will use shifted partials after doing some transformations, since the set of monomials we are assuming is small, the union of the support. So we need to utilize the sparsity of Qij's. So for example, there may be a monomial like x1 dot dot x d, right? So this is a degree d monomial, and it has maximum possible support, and this is the reason why B could be D. B could be as high as D, right? So can you think of a way to reduce B by applying a transformation? When you look at the monomial x1 dot dot xd, which is making B equal to D, can you think of a transformation that reduces the associated parameter B below D? You apply that transformation on x1 dot dot xd, and well, essentially some of the variables get killed. So variable restriction, right? So if we try the idea of restricting the variables to constants, then potentially these high supported monomials will become low supported, and that will reduce B. So we'll try then random restrictions. So we'll show using random restrictions that Qij's can be reduced to a sum of square root D support monomials. Okay, so we'll basically killing some variables, and the advantage will be B will come down to square root D, and then we can use shifted partials as before. So let us prove that lemma formally. First state it. So this is let f be an n variate d degree polynomial computable by a size s less than equal to C is some constant yet to be fixed, and assume that f is a polynomial that is computable in size n to the square root d, homogeneous depth 4. Circuit C. Let rho be a random restriction that sets each variable to 0 with probability 1 minus n to the minus 2c. Point being that it's a high probability. Okay, so rho is a random restriction which will set a variable to 0 with probability very close to 1.
So randomization is over variables and number of variables.
No, randomization is just on the bits that rho uses. When you give x1 to rho, it will flip coins to decide whether to set it to 0 or leave it free. It is just the biasness of its coin.
Yeah, so it is over a subset of the number of variables.
Not variables. It's over its own randomness. It has nothing to do with the variable. It depends on what it has in its mind. It's not external to it. So use this process rho on all the variables. So rho x1, rho x2, dot dot rho xn. The motivating case is again a monomial. So a monomial that has a lot of variables, right, that has a extremely high chance of being set to 0. And a monomial that has very few variables will be able to escape from becoming 0. So then with probability greater than or equal to 1 minus 1 over s, the polynomial rho of f what is rho of f? Well, rho of f is just apply rho on each variable. So this polynomial is computable by a homogeneous depth 4 C prime with bottom product fan-in less than or equal to square root d and size less than or equal to s. Okay, so note that now we are talking about size and not just the top fan-in. So we are counting the monomials also. So there were overall S monomials that you can see in the circuit C, and when you apply this transformation rho, then random transformation rho, then with probability 1 minus 1 over S, only those monomials will survive that have support square root d. Actually, this should be not just product fan-in but support. It's a stronger thing. bound on the support of these monomials that you see. No, it's a weaker thing. Yeah, so support is small, but the individual degrees may still be high. Yeah, we still have not gotten to b less than equal to square root d. So b can still be high. We have just reduced the support with this, right? So this is believable. Probabilistically, this should happen. Of course, the parameters we have to carefully see. Why are we getting square root d here? So that is a short proof. Is the statement clear? No. Yes. Okay.
So this lemma kind of allows us that if we have like a gate where there's a lot of, let's say a large number of polynomials, then we can, by the standard restrictions, we have smaller, more sparse polynomials. But like in our model, like the sparsity is like almost given for free, right?
What do you mean given for free?
It's told that like the QIJs are homogeneous sparse polynomials.
Right.
So why are we doing this?
I do not understand that.
So here it is given
The sum of the sparsity is S. The definition of S is sum of the sparsity of all the QIJs is S. And we are working with S. That's our size parameter. And the probabilities here are all with respect to the process row. Yeah, so once we have proven this lemma, then probabilistically we can think of the model being somehow weakened, but it is still not clear whether b, we can say that b is less than equal to square root d. Right, so it is still not clear how will we use the upper bound of shifted partials. But anyways, we'll see how to do that next. Let us first do the proof. So the proof of this is, so among all these QIJs, collect the bad monomials, right? So among all QIJs, consider the monomials M1 to MR that have support greater than root d. How big can R be? S is everything, so R is less than equal to S. So now for one monomial Mi, what is the chance of non-vanishing? So Mi is a monomial that has more than square root d variables. So what is the probability of this being not set to 0? Every variable should be left free, right? And that happens with probability n to the minus 2c. So you multiply those probabilities. So you get this. And this is for every I 1 to R. Is that clear? So now what is the probability that there exists an I? There is an Mi which was not set to 0 by rho and is bad, right? So that is less than equal to this probability times R, right? That's the union bound. R is at most S, which is at most n to the c root d, right? So this is less than equal to n to the minus c root d, which is smaller than 1 by S. So the probability that some bad monomial survives rho is smaller than 1 by S. So hence we have shown that with probability greater than 1 minus 1 by S, all the large support monomials vanish. Monomials in Qij's vanish. Yeah, so this is a simple argument. So now the monomials that remain are low support, square root d support. But we are still not in a position to use the upper bound for shifted partials, right? Because the b is not small. So we'll slightly change that measure. So now we need to find or define a measure that is small. For such sigma pi models. Yes, so any ideas how do we modify shifted partials so that it works for support and not degree? Well, what is the difference between low support and low degree? Why does the degree increase? Because of individual degree greater than 1. So why not just force the monomials to be multilinear? Then the support and degree will be the same, right? So that is all. That is what we'll do. So since we will prove a lower bound for a multilinear f, anyways, I mean our goal or objective polynomial is already multilinear. So if we impose multilinearity also on the monomials, then the support becomes the degree, right? So this is not in conflict with our final application. So we can pick a measure that ignores the non-multilinear monomials or ignores the square full monomials. So let us just give the definition of the measure in full. So
you just kind of compute the derivative with respect to like each variable, and if you set to 0, and if it becomes 0, then that is a square term.
No, so I'll now give the definition of the measure. A measure that works for any polynomial. Polynomial will not be restricted. It will be a modification of shifted partial. So for any KL and polynomial fx bar, so what the authors define is called projected shifted partials. Who are the authors? This will be KLSS 2014. So Kayal, Lemay, Saha, Saptrishi. You saw all of them, didn't you? Yeah, Lemay was not there. Okay, you saw 3 of them. So okay. So projected shifted partials. PSP KLF. Yeah, it is called projected because even when you are looking at a squareful monomial like x1 square, you project it down to x1. I mean, basically you go modulo the ideal x1 square minus x1. So you project x1 square to x1. So the exponent is just made 1 if it was not 0. If the exponent was 0, then you don't do anything. Right? So it's this type of a projection that we want to use. So the result will definitely be multilinear. So this is the F span of the set of polynomials where so we'll do similar thing. We'll first differentiate f and then we'll multiply it by a monomial, and then whatever we get we'll make it we'll project it down to multilinear. So multilinear projection. Okay, so this is the action on shifted partials. So degree of M1 is L. In this case we are taking it exactly L. I'm not sure whether, let's make it less than equal to like before, and degree of M2 is k order derivatives, and there is no point taking M1 M2 square full because we are going to project. So we'll take M1 M2 to be multilinear.
M2 multilinear. Why would M2 multilinear? We'll take the partial derivatives.
Yeah, that also we have taken multilinear. It will work.
Doing operations but commute, like taking the derivative with respect to a monomial and going by that.
Yeah, sure. Yeah, there are these objections, but it will work.
Yeah.
I think it does not matter. Okay, so where this multilinear projection operator, so this refers to the projection mod x1 square minus x1 dot dot, that is just a projection or a restriction to this ideal. Oh no, that's not what it is. It's actually the multilinear part. So square full will be sent to 0. Refers to the projection to the multilinear part.
This model x square.
So this is exactly. So remainder modulo x1 square dot dot xn square. It's slightly different. So x1 square will actually be sent to 0. You have to ignore the square full monomials. So this is really extracting the multilinear part. Also, taking M2 multilinear is justified because your f, target f is multilinear. So if you will differentiate determinant by x1 square, you will anyways get 0. So you don't get mileage on the lower bound side. So there is no point using anything else as M2. Yeah, M1 is different. There is an advantage if you had taken M1 non-multilinear or general. But then since here we are using this mult operator, if you multiply by x1 square again, this will not contribute. Mult will kill it to 0. So yeah, both the things are justified. So finally, the measure will be dimension of this space. So the measure gamma projected shifted partials with parameters KL of a polynomial f. Right, this gamma measure is the dimension of PSP KLF space over the base field F, dimension of this vector space. Is this clear? Okay, so this is the modification on shifted partials, and its motivation is the previous lemma where we randomly restrict the variables. So it is good for proving an upper bound, because in any Qij, if you have x1 square appearing, it will not contribute anything to the measure. So the upper bound will come out to be small, which is the correct thing to have. And on the in the side of the lower bound, since you are working with determinant, taking m1 m2 multilinear would be enough. So lower bound you cannot really jack up by taking more m1 or more m2. So that's the rough motivation. Yes, let us quantitatively do this. Let's do the upper bound. What expression do you get? So let f be an n variate d degree polynomial computed by homogeneous sigma pi of bottom support less than equal to R. So all the Qij's we are assuming have monomials of support at most R, and total size is S of the circuit. So then the upper bound is projected shifted partials measure on F, K, L parameters is so S for the upper bound on the number of product gates, top product gates, and each product gate will essentially give you the same thing that you got for shifted partials. With minor changes here and there. So if you remember, this was with A plus K, choose K, right? So that A we have replaced by D by R, which, I mean, A is not actually bounded by D by R, but in the proof we will see that the measure will still have this expression instead of A. And the second expression was that was something like n plus bk plus L, choose n, right? So which is also bk, which is also this bk plus L. Yeah, so how will that change to this? So this will basically be because of the fact that we are now only looking at multilinear monomials. In shifted partials, we were looking at more general monomials whose degree could become n plus bk plus L. But now the degree won't matter. So now actually the top part will remain n. This bk plus L will go away. And this bk plus L will continue to be there with b replaced by R. So we are getting rk plus L essentially.
there to make a general monomial, we are choosing the variable by repetition.
Right.
This is why in upper part it is added.
Yeah. Yeah. So those are the changes. So it's a similar expression. This is again expected to be large. This is again expected to be. I mean, it is exponentially large, but still in relation to the lower bound for determinant, this will be small. It's a similar. The comparison will be very similar to what we did in the previous proof for depth 4. Right. So that's the idea. So let's just complete this. So consider a product gate qi1 dot qia. We could assume individual degree of any variable or every variable in qij to be less than equal to 2. Why is that? What if you have a x1 cube sitting in qij?
Yeah, it is.
Sorry?
That measure will send it to.
But that is also true for x1 square. So why am I keeping x1 square? So just a small point is that x1 square, when you differentiate by x1, you get x1. So that x1 will contribute. But x1 cube, when you differentiate by x1, you will get x1 square, which will not contribute. So this is why we'll keep 2 but nothing beyond. So this is without loss of generality. So let me write down the point. So point is that for a multilinear M2, when you differentiate x1 cube, you get something non-multilinear. And since you get something non-multilinear, when you apply the mult operator, you get 0. So such things have no contribution whatsoever to the measure. And remember, we are proving an upper bound, right? So we have to be careful about counting everything. So up to beyond 2 we are fine in ignoring, but 2 we cannot ignore. Also, we can assume without loss of generality that degree of qij is at least r and at most 4r. So why is that? So why is the degree of qij at most 4r?
There are two pi. Sigma pi, sigma pi.
No, in qij look at the monomials. So how can you say that each monomial has degree at most 4r? Well, because of bottom support r, we can take 2r, right? Yeah. So why am I taking 4r? Yeah, I'm not sure. So this should be 2r, I think. Okay, and oh no, I think it will. Yeah, that 4r would probably come. So for the other side, how can you say that the degree of qij is at least r? No. If it is less than r, then you just multiply qij with the next one. You keep multiplying them till you get to degree r, till you cross degree r, right? But when you do this process, now what is the upper bound?
3r.
3R, right? Yeah, it could be more than 2R. I think 4R is also possible.
I mean, for 4R you have to multiply two things of degree.
Yeah, so let us just keep it simple and go back to 4R. It's because of this process. So I want simultaneously the degree of Qij to be R to 4R, and that can be achieved by just multiplying out things if needed. If the degree is too low, then you just multiply things.
You have, and the usual degree is 2, so you have a monomer that has degree 2 in everything.
Okay, good. So now we have these bounds on degree of Qij. Which is really now the bound on B, right? So with this we know that B is at most 4R, but we also know that B is at least R. So since B is at least R, and this is a homogeneous model, right? So what could A be? To compute degree D monomial, A could at most be D by R, right? So that's a bound on both. To the case of sigma pi A, sigma pi B, with B less than equal to 4R and A less than equal to D by R. Is that clear? So now we are in this R and D by R product famine, so we can just repeat the proof of shifted partials upper bound.
So in the lemma statement, that sigma pi, sigma pi, sigma pi A, sigma pi B. In lemma statement,
Okay.
that homogeneous sigma pi A, sigma pi B.
No, A, B I have defined here. It is now defined here, where A is less than equal to D by R and B is less than equal to 4R. This we get because of the measure definition. So for the purposes of proving upper bound, we get these assumptions. Originally the product findings could have been arbitrary. Yeah, so in a way, only those product gates contribute that are well behaved. Other product gates we just ignore because they will not contribute to the measure. Yeah, so finally by using the multilinearity projection, by using the multilinearity projection, we can redo the proof of shifted partials upper bound. So shifted partials lemma 1. So when you do that, you will get this bound. Okay, A is D by R and B is 4R, and moreover this n plus Bk plus L goes away, just n remains. Is that clear? Yeah, so that's the upper bound. Now for the lower bound, you have to show that under these projections rho, gamma should come out to be large, right? So that for some reasons is not has not been done for determinant. So polynomials that are more complicated were used. So if you do random restriction on determinant, then I think it vanishes. because if you just kill a row, then it's gone.
What is there was this parameter C, right?
Mhm.
Yeah. So roughly what?
So C is a constant.
So,
Just that the size is smaller than n to the C root d.
but then what we see, the constant will matter, right? Because it's the exponent. So the probability of killing a row in the determinant will sort of depend on C, right?
Yes, but the probability was very high. It was nearly 1 of setting something to 0. So with such a high probability, you, I think, usually would just kill a row, and once you have killed a row, you are done. So determinant is too sensitive, and permanent also is too sensitive to this measure, to this variable restriction. So other polynomials will be used that are not so sensitive. So the lower bound is trickier. And doesn't work for determinant permanent. So some new polynomials are invented. So currently results are known for two families of polynomials. So one is the iterated matrix multiplication, because that clearly is completely insensitive to variable restrictions, because you are multiplying these n cross n matrices. Even if you kill many rows or many columns, it doesn't change iterated matrix multiplication much, right? It still survives, and you can talk about its shifted partials. The iterated matrix multiplication polynomial. So what is that? That is just multiply D matrices and look at the corner 1,1 entry. That's a polynomial. So where Mk is the matrix Kij n cross n. So each Mk, k from 1 to d, is a matrix, n cross n matrix, where you can identify the variables as x, k, I, j. So you multiply them. Right. So this is n square d variate and d degree. Yeah, and there is another polynomial which has been used in this in these sequence of results, which is called the Nissan-Wigderson polynomial. So the thing is that this is the first polynomial is better because this is in VBP, not just in VP but in VBP, right? It's a very I mean, in the hierarchy of things, it's a very easy polynomial. Nissan-Wigderson polynomial is more like permanent. It generalizes permanent. So all we could say is that this will be in VNP. So it will be a much harder polynomial. So when you prove a lower bound for IMM versus when you prove it for Nissan-Wigderson, there is a difference in the quality. Right? So IMM results are more interesting because it's an easier polynomial and you are proving a lower bound. Nissan-Wigderson polynomial anyways seems quite hard. But initial results were proved for this because the lower bound techniques are nicer here to analyze. So the way this is defined is there are three parameters n, m, k, and there are nm variables. So think of it as an n cross m matrix. And like permanent, it is a sum of huge number of monomials. So 1 comma p1 n comma pn, right. So in the case of permanent, p is a permutation. In here, p will be a polynomial. It's a polynomial map. So you in fact go over all the polynomials. And what is Fm? Fm is a finite field. So over Fm is a finite field of size m. So Pt of degree k. Yeah, so once you restrict the degree of p, since you are over a finite field, there are finitely many polynomials. Use all of them and sum up these permanent kind of monomials. So that is the Nissan-Wigderson function. Now, where can you put it? What is an algebraic complexity class that contains this? Why is VNP obvious?
Exponential sum of small size circuits. These problems will be
BNP should be an exponential sum of a single circuit.
yes, and then you restrict.
So you'll have to first construct a circuit whose restrictions are all of these. I mean, that shouldn't be too hard, but
Yeah.
it's not obvious, right?
No, it's not obvious. If it is obvious, then you are making a mistake. So it is worthy of an exercise. Yes, maybe. Yeah. Next is. I think I forgot to give or state this variance criterion. If a polynomial's coefficient is Sharpe/Poly computable, then it is in VNP.
Is that easy?
I did not state it, right? Yeah. So that should also be.
How hard is
That should be an assignment. So using that, you get this immediately. Follows from variance criterion. I don't know how you will get it otherwise, actually. Yeah, so if you are given sum of monomials where there is an easy way to extract coefficient given a monomial, where easy is actually defined in a very relaxed way. It's not polynomial time algorithm, it's Sharpe/Poly. So in particular, you can use permanent and other very hard algorithms. So using those hard algorithms, NP hard algorithms, if you can extract a coefficient of a given monomial, then that polynomial is in VNP. So it's a pretty useful criterion. In particular, this it will immediately follow that NW is in VNP. And it's an open question whether anything better holds. So is NW in VP? That's an open question.
some assumptions on NM and K?
Like NM is the number of variables, it's a family. We never talk about a single polynomial in VNP. It's an infinite family of polynomials. So for these polynomials, what are the results known? Upper bound you have seen. Now for the lower bound, you have to really work with the special properties of these polynomials. So those things I am completely skipping. That will take several lectures. So I think at this point you know the techniques and you can just go and read if you want to read the proof from Ramprasad's survey. So I'll just finish off with the final theorem statements. Showing you all those calculations I think will not serve much purpose, and also with the risk of making you bored. So over characteristic 0, homogeneous sigma pi complexity of Nissan-Wigderson polynomial with parameters d cube d by 3. So these are the NMK, they are comparable, is d to the omega root d. So what is the degree of this? That's d, right? It's a degree d polynomial on d to the 4 variables. And for that you are getting d raised to square root d, which is good, right? So it's a result comparable to what you got for sigma pi root d model. It's a comparable result, and then this was improved by KS14. So this case is Kumar and Saraf. So here characteristic 0 is needed because the lower bound goes through some real analysis. So Kumar Saraf then proved it for all fields. So above holds for all fields F. So no restriction on the characteristic. Further, they proved it for a better polynomial. So this IMM. Its complexity is d to the square root d. So IMM is a polynomial of degree d, and you are getting, and n will be assumed to be poly d. So the number of variables is also d cube or d4, whatever. So again d raised to square root d is a good bound. So yeah, these are the results which you will get ultimately. So proofs are being left. So proofs can be read from Ramprasad's survey. Right. Any other questions? Okay.